All right, hello chemistry family. Going to be working through the book problems for chapter 13, starting with number 12. So number 12 is right here. Let me zoom in a little bit. 12 says consider an initial mixture of N2 and H2 gases that can be represented as follows. The gases react to form ammonia gas as represented by the following concentration profile. So here's the profile. It will each plot on the graph as N2, H2, or NH3. Explain your answers. So, on this, the green line that has the highest concentration, which is this, is going to be H2. And I know that because 1, 2, 3, 4, 5, 6, there's more H2 than N2. And I also know that H2 is the small one because H2 is smaller than N2. So the blue one is N2 because I start with some less. I actually have 1, 2, 3, 4, 5, 6, only 2 of these. So I have 3 times more H2 than N2. And the line that I have none of to begin with is NH3. NH3. So that's my labels. Explain the relative shapes of the plots. Well, I just did. H2 and N2 are reactants, so you start with them. There's more H2 than N2. When is equilibrium reached? It's reached right here. How do I know? Well, that's when everything's flat, so my forward reaction and my backward reaction are constant. So that is number 12. Okay. Moving on to number 15. So here's my trusty dusty notebook. What is Blue's Clues? Handy dandy notebook. I don't know if you guys even get that reference. Wow. Suppose a reaction, this is number 15, has an equilibrium constant of K equals 1.3 times 10 to the 8th. Wow, that's big. What does the magnitude of this constant tell you about the relative concentration of products and reactants that will be present at equilibrium once it's reached? Is this reaction likely to be a good source of products? Well, this K is much, much, much greater than 1. Which means that we know that K is equal to products over reactants, right? So in order to get a huge K, that means there has to be a huge concentration of products at equilibrium. So, products. So at equilibrium, a lot of products. At equilibrium, a lot of products. That's 15. Moving on to 27. 27, we have, at a given temperature, K, is 1.3 times 10 to the negative second for the reaction. So, on 27, I have K equals 1.3 times 10 to the negative second. And the reaction is N2 gas plus 3 H2 gas is in equilibrium with 2 NH3 gas. And really this should be Kp because these are all gases. Calculate the values of K for the following reactions at this temperature. So on 27, I have different reactions for sure. So I'm going to do letter A first. Well, actually, I'm just going to look at my first reaction. My first reaction is N2. Here's A. So to compare, A is 1/2 N2 plus 3/2 H2 is in equilibrium with NH3. So from the notes, I divided this all in half. So when I divide in half, that means I have to raise my k to the 1/2 power. So for A, 1.3 times 10 to the negative second, that whole thing to the power of 1/2, which is also the same as square root, is equal to 0.11. That's A. For B, I flipped it. For B, I have 2 NH3 is in equilibrium with N2 plus 3H2. So when you flip it, I have to do 1 over K. To do 1 over K. So this is going to be 1 over 1.3 times 10 to the negative second. And that ends up giving you 77. So there's B. A, B. For C, let's see, what did I do? I flipped it and I divided it by half, because on C, I have NH3 is in equilibrium with 1/2 N2 plus 3/2 H2. So that means it's going to be still 1 over K to the power of 1/2. So that means 1 over 1.3 times 10 to the negative second, that whole thing, square root for C. And on that, you should end up with 8.8. And then that leaves us D. For D, I have 1/2 H2 plus 1/2 Br2 is in equilibrium with HBr. So on this one, what did we do here? On D, I have half, and I have half. So on this one, I'm dividing everything by 2. Wait a second, how is this? Oh wait, no, this is weird. Am I on the right question? Nope. That's why. Wow. I'm at the wrong question. On this one, I was on the wrong question. I have 2, this makes more sense, N2 plus 6 H2 is in equilibrium with 4 NH3. So on this one, I multiplied the whole thing by, by 2. So if I multiply my K by 2, I'm actually going to raise the K to the second power. I'll show you why. Because now I have NH3 to the 4th over N2 to the 2nd over H2 to the 6th. So that means I'm going to raise my whole K to the 2nd. So my K squared is equal to 1.3 times 10 to the negative second, that whole thing squared, almost off the screen, and that equals 1.7 times 10 to the negative 4th. So that question was straight out of the notes. That was 27. All right, let's hydrate a bit. And let's move on to number 31. On 31, this looks like I've got some molarity. So On 31, at a particular temperature, a 3-liter flask contains 2.4 moles of Cl2. So, here's my flask. Oh boy, this is a great picture. I have 3.0 liters that has 2.4 moles of, this is Cl2. Oh boy, didn't draw this big enough. I'm just gonna write everything out because there's more than one thing. Wow, I should have read this before. I have a 3-liter flask that has the following. Has 2.4 moles of Cl2. It has 1.0 mole of NaCl. And it has 4.5 times 10 to the negative third moles of NO. And then it says, calculate K for the following reaction. So I have 2 NaCl gas, and this should really be Kp, is in equilibrium. Well, no, this wouldn't be Kp because I've got molar. So, nope, wrong. 2 NaCl gas is in equilibrium with 2 NO gas plus Cl2 gas. So I know that K is going to be equal to NO squared times Cl2, there's my products, over NaCl squared. So there's my K expression. Now I need to get the molar for all of these. So for the first one, for Cl2 moles per liter, it is going to be, let's see. Well, let's do NO first. Might as well do NO first because it's the first one I need. That's going to be, well, it doesn't matter. We'll do Cl2 first. I have 2.4 moles divided by 3 liters. Put that in your calculator. So Cl2 is 0.80 molar. For NaCl, I have 1 mole per 3 liters. So that's going to give you 0.33 molar. And lastly, for NO, I have 4.5 times 10 to the negative third moles per 3 liters. So on this one, that gives you 1.5 times 10 to the negative third molar. Now, I'm going to sub all of those in to my K expression. So here's my K expression. So K equals, for NO, I'm going to have 1.5 times 10 to the negative third, that's going to be squared, times Cl2, 0.80 molar, divided by 0.33 molar squared. So K, once you multiply that all through, ends up being 1.7 times 10 to the negative fifth, no units. That is 31. That's 31. Okay, we're moving here. Happy with how many I've got done so far. 33. All right, finally a KP. On 33, the following equilibrium pressures at a certain temperature were observed. So this reaction is 2NO2 gas is in equilibrium with 2NO gas plus O2 gas. Whenever you have pressure, so they give me P NO2 equals 0.55 atm. They give me P NO equals 6.5 times 10 to the negative fifth ATM. That's small. And PO2 is 4.5 times 10 to the negative fifth ATM. Whenever they give you pressures, see, I'm so, what's the word, alert to this. You have to show work with parentheses. And you know what? These shouldn't have even been parentheses. These should have been brackets up here because this was still concentrations. This is why I'm so like, about this. Because a couple of years ago, so this is something I learned my first year in person at the AP grading. I think I told you this in class too. But you have to have parentheses for pressures. So parentheses, pressures, P, parenthesis, P, pressure. That's how I remember it. 33 says calculate Kp. So Kp is going to equal parentheses the pressure of NO squared, parentheses pressure of O2 over parentheses NO2 squared. If you don't write parentheses, you literally will not get the points, which is stupid, but that's what you got to do. That's what you got to do. Or you could have written it like this. You could have said Kp equals P squared NO times PO2 over P squared, that got weird, over P squared NO2. You just have to prove that you know that you're dealing with pressures somehow. Sub in the work. This is a really easy plug and chug. So Kp ends up equaling, sub all these in. So I'm going to have 6.5 times 10 to the negative fifth parentheses squared times 4.5 times 10 to the negative fifth parentheses over NO2 is 0.55 parentheses squared. So the same as everything else, but you have to have parentheses for Kp. So Kp, when you put that in your calculator, ends up being 6.3 times 10 to the negative 13th. That is 33. Moving on. We are cruising to number 45. Oh, I'm going to need a war room for this one, I think. Let's be the last one for this recording. All right, 45. The equilibrium constant, K, equals 0.0900 at 25 degrees Celsius for the following reaction. H2O, gas, plus Cl2, O, gas, is in equilibrium with 2HOCl. You know what? This is going to be a pretty... Nah, it's fine. I'll just do it quick. So 45 says, for which of the following sets of conditions is the system at equilibrium? For those that are not at equilibrium, in which direction will the system shift? So here is where I've got K, and I have to compare my K to Q. Oh, you know what? We'll have to finish this later. I'm here. Hold on.